Okay, so welcome to this next video in the Theory of Probability playlist. In this video, what we're going to do is look at the convolution of two gamma distributions, and we're going to use it to find, amazingly, what we're going to find is we're going to find the normalizing constant for the general beta distribution. Okay, so let's begin. So, let's say we have two random variables, x and y, okay? So x and y, which are both gamma distributed, and they both have the same lambda parameter, but they have different parameters in this position, this first parameter. So this one is x is distributed gamma a lambda, and the second one is y is distributed gamma, and let's say this one is distributed gamma b lambda. Okay, so an example in which you can think about, an example which we'll come back to in the next topic, is you can think about going back to our email example. So we start off at time 0 and you go on, and you have all possibilities for how you receive emails. So we have ... Now, if a and b are integer values, in fact they have to be positive integer values. If they're positive integer values, then what you can think of these as being is x you can think of as representing the probability well, you can think of x as being the random variable which is going to ascribe each one of these outcomes where you're receiving emails. It's going to ascribe each outcome the time at which the 8th email arrives. Time at which the 8th email arrives. Okay? And similarly, you could think about y as being the time at which the bth email arrives. Of course, that's only a good intuition to have if a and b are integers. And in fact, we're going to take the convolution in a much more general case than that. We're going to take the convolution in the case where a and b are just any positive real numbers. Okay, but it's a good intuition to think about. This is the best storyline that you can come up with for what the gamma distribution means. Okay, and then let's think about this y distribution also being here. But in fact, there is a better way to think about the y than just being the time at which the bth email arrives. Because think about what we're going to now construct. The next thing we're going to construct is the convolution of the two. We're going to construct x plus y, also known as the convolution of the two random variables. So, if you want to have an intuitive notion of what it means to add the two together, then it would be a good idea for y, instead of mapping you onto the time at which the bth email arrives, it would be a good idea for y to map you onto the time at which the a plus bth email arrives. So sorry, time at which the a plus bth email arrives. So I'll put a plus bth email arrives, but then you subtract off the time at which the 8th email arrives, i.e. to define y to be x plus y, subtract off x. That would be a very clever way of doing it, to intuitively think of it. So I'll give you some more intuition as that once I've just written it down. Time at which a plus bth email arrives, and then subtract off time at which the 8th email arrives. Time at which the 8th email arrives. Okay, so let me give you a picture of what I mean by that. Email arrives. What this, so if we have here, let's say a was equal to 4, so this is the time at which the 8th email arrives. Now, instead of thinking about y as being the time at which the bth email arrives, so let's say b was 5, y would map you onto that if you thought about that. But instead, let's think about y as mapping you onto the time at which the bth email after the 8th email arrives. So, in other words, basically, imagine going along with this problem and waiting until the 8th email arrives, but then instead of just waiting then for the bth email to arrive, instead, imagine setting the clock back to 0, and imagine setting the number of emails you receive back to 0, and starting the problem again, and saying, okay, now let's wait for the bth email. So let's wait for the bth email after the 8th email to arrive. So not the bth email from the beginning to arrive, but the bth email to arrive from the 8th email. So if we imagine b was 5, this will in fact be the 5th email after the 4th email. So you'll go 1, 2, 3, let's draw some more. 3, 4, 5. So instead of being the 5th email after the beginning, it would be the 5th email after the 8th email has arrived. And if you think about it, it's exactly the same problem, just the symmetry of the problem, the independence of the interval up from 0 to the time at which the 8th email arrives, and then the 8th email time from when the 8th email arrives onwards. It's completely independent. So the problem effectively goes back to the original problem. So y is still going to be gamma distributed b lambda, as long as what you mean by y is not the time at which the bth email arrives from 0. What you mean by y is the time at which the bth email after the 8th email arrives, when you've reset the clock basically to 0 at A. So it's basically the time at which the A plus bth email arrives. So over here, so the A plus bth email when you're counting the emails from the start, which just means the bth email after the 8th email, and then you take the time at which that arrives from the start and subtract off the time at which the 8th email arrives, and that will tell you how much time there was between the 8th email arriving and the A plus bth email arriving. So that is what you can think of y as being, and that's a very good intuitive way to picture what y is, because then x plus y, this new random variable, is extremely intuitive, because x just maps you onto the amount of time from the beginning till the 8th email arrives, and y just maps you onto the time from starting at the 8th email till when the bth email after the 8th email arrives. It basically maps you onto the time between the 8th email and the bth email to arrive after the 8th email arriving, basically. It maps you onto... So y is going to give you this time here, basically, and x is going to give you this time here, basically. So I'll highlight them. So this is x, this is y, and of course there are lots of other outcomes in this probability space. That was just one of them. This probability space contains every possible outcome for how the emails can arrive. Okay, so it's pretty obvious what x plus y is going to do. It's just going to add this orange one to this green one, and it's going to tell you from the beginning time what time does the a plus bth email arrive. So it's going to tell you x plus y is going to map each outcome onto the time, and I'll just put of a plus bth email. Okay? Right, and then from that argument, it's intuitively obvious how x plus y is going to be distributed. It's going to be distributed gamma as well, because remember we saw in the previous video that if you want to know how the random variable which tells you the time at which a certain email arrives, it's just going to be gamma distributed. So x plus y is going to be gamma distributed. Now what email are you waiting for? You're waiting for the a plus bth email, and again the lambda, remember, the lambda is the parameter, it's the rate parameter, it's the expected rate at which emails will arrive. So you multiply, so basically, if you expect to receive 3 emails every minute, if that's the average number of emails you receive every minute, that's what lambda will be, if you're measuring time in minutes, of course. So it's, given the way in which you're measuring time, what is the rate according to that measure of time of emails that you receive per unit in that unit of time. Okay, so that's what x plus y is going to be intuitively. So that's what the convolution is going to be from this intuitive argument of, or in terms of where a and b are viewed as being positive integer values, and you can think of them as attaching the times, you know, as being random variables attaching the time at which the a female and the b female after the a female arrive, basically. Okay, but what we're going to see is that this basically still holds true, this statement here, that the convolution of the two random variables x and y is in fact distributed like that, even if a and b are just arbitrary real numbers. Okay, so the argument, we can't do it in the same intuitive way. Instead, what we have to do is go back to our original ways of dealing with convolution. And in the next video, what we'll do is recap how to do convolutions for more abstract probability spaces where we can't just do it from a story like this. And we will find that the convolution is in fact equal to this.